Our next speaker is Brett Koonce, and he's going to talk about Swift for TensorFlow. So I'm excited for this. Please welcome Brett Koonce.
Hello. Thank you all for coming. Thanks to AltConf for having me. Today we're going to talk about Swift for TensorFlow. Very broadly, I spent the past few months getting up to speed on all of this. I've decided that this is how I'm going to be doing things going forward. The purpose of my presentation, then, is to convince you to do the same. Towards that end, we'll sort of ask the question of why we would want to combine these two tools, sort of how we got here. Then we'll zoom out a little bit, sort of look at where I think things are going down the road. Then we'll look at what we, that is to say, Swift iOS programmers, bring, or perhaps more broadly, mobile programmers in general, bring to the table. And then I'll show you what I think the best way to get started with this whole thing is, and then we'll do a quick recap. So here we go. I usually put comics in my presentations, so today I have a bunch of stuff from Calvin and Hobbes. If you don't like Calvin and Hobbes, I feel sorry for you. Why TensorFlow? I think actually the broader question, and one that you can spend a little bit of time on, is why GPUs? Your computer has a perfectly good CPU in it, so why are we using your video card to do math? I think if you look back at the history of computing and you go back into the 80s or so, and you look at Cray, what he was convinced that the future of supercomputing was what was going to be called vector processing. You had this concept of SIMD, single instruction, multiple data. If you look at the current generation of NVIDIA RTX video cards, they all do ray tracing. You might think of each pixel on the screen as having a little bitty ray tracing program, and then your whole view or scene that you're seeing as a large collection of data. So then for every single pixel, 4,000 across by 2,000 down, you're literally running a separate thread in order to render what that particular pixel is seeing every single frame. And so this is kind of very much millions of threads are being executed every second. It's very much the same concept, I think, if you were to go back in time and show it to Seymour Cray. These cores, then, in these video cards, it's easy to parallelize this approach, so you can throw lots of cores at these problems. So the cores in your video thing, modern video cards have like 5,000 cores, and even like 10,000 core designs are currently being discussed. So this is an approach that scales. You know, the cores are slower but not as powerful, but there's a lot of them. The second piece of the puzzle, I think, is the GPU memory subsystem. If you study the history of high-performance computing, a lot of it's actually less about processors and more about how they talk together. So the memory subsystem inside your video card is literally an order of magnitude faster than the RAM in your computer. And so this is another reason why we want to do things on a video card. So roughly a decade ago, doing things on a video card even became remotely feasible, and so people started trying to build these frameworks in order to work with this stuff. So literally there were a dozen frameworks that exploded, some from academia, some from the industry, but out of them all, TensorFlow has kind of become the 600-pound gorilla of this ecosystem, we'll say. TensorFlow itself, proper, is written in C++, which is user-friendly, but it's very picky about who its friends are. So one of the first things that was invented for TensorFlow was Keras, which is sort of this high-level Python wrapper to sort of make dealing with it a lot less painful. Google has sort of embraced Keras, and it's become kind of part of the whole thing. And the last year or two has been sort of them trying to find a happy medium between these two ecosystems. Part of the reason why I think broadly Google has been able to succeed on this front is they have sort of what I would call like an iron triangle. Machine learning is extremely important to Google, and so it literally drives the bottom line over there, so they're able to throw a lot of resources at all this. They have this whole Google Brain team that's always publishing interesting new research, and alongside their research, they always publish new models in TensorFlow, and so this makes their whole ecosystem very sticky because people are literally every day downloading their stuff and trying it out. And then the third and final thing, and this is something people are less aware of, but a lot of this machine learning stuff actually breaks with some regularity. And so Google has a whole army of engineers running around in the background, hitting on things with hammers in order to create this illusion that it's all perfectly smooth and seamless. There's other companies in this space, but they may have resources and engineering, but they don't necessarily do the research. They have 2 of these 3 things, but Google is the one, I think, that has literally a lock on each of these things, and that's why they're so successful. Why Swift? Well, hopefully I don't have to evangelize Swift here. This year, Swift came out 5 years ago. This year, to me, has been the year where my old crufty Objective-C programmer friends have come up to me and started saying, I think there might be something to this whole Swift thing after all. So at one point, there was a company called NextStep. They wanted to write an operating system. They wanted to use a programming language called Smalltalk. Smalltalk wasn't very fast, so they wrote a set of bindings for the C language to sort of bring the Smalltalk ideas to C. That was called Objective-C. In order to do so, they then forked a compiler called GCC out of the Free Software Foundation. This is a subject I'll try to reduce down very quickly in a few seconds, but we'll say that the RMS, one of the key people, one of the Free Software Foundation founders felt, we'll say, and probably correctly so, the compiler is one of the key technologies of the open source movement, and so he made sure that they had a lock on, they were actively resisted outside interference, we'll say. As a result, I think they created an opportunity for another open source compiler to come into this whole ecosystem, which is what happened whenever Apple threw their weight behind LLVM out of the University of Illinois with Chris Lattner. If you think of your program as being like a collection of instructions, you might take, the first time a variable, you might make a list of all the spots where the variable is accessed, and by extension, you can make a graph. Then you can go to this graph, go before the very first instruction, put a malloc, and after the last one, and put a free. This is kind of the basic idea of how automatic reference counting works, which is one of the first technologies that LLVM introduced into the C world. In the same vein, you can do this sort of graph traversal trick with closures, and so they introduced thread safety checks there for a while. The problem with this, though, is they were retrofitting these changes on top of C, and there's a limit to how far they could push this technology. So then, 4 years ago, they announced it here at WWDC up north, but they announced Swift, which brought full-blown functional programming into the iOS ecosystem. I would argue that Swift is in many ways not a revolutionary language. It's a fairly pragmatic language that sort of takes ideas from many other programming languages and puts them into a coherent, unified whole. It's designed to work side by side with Objective-C. It doesn't really force you to completely change your paradigms or whatever. But I think this is part of why it's been a success. It's allowed, crusty, imperative programmers like myself to sort of look at it and squint and say, this looks reasonably similar to what I'm used to. But then, I think about 6 months to a year in, you start to realize that, oh, there's something a little bit different here. And for me personally, I went back at one point, I coded for Swift on a project for a little bit, and I started going back and messing with some old Objective-C code for a project that I hadn't touched in a while. I started staring at all this memory code and all this various stuff, and I realized, oh, I haven't even thought about this, for a while. And so, to me, that's what's cool about this whole Swift thing, I think, is there's a whole new generation of programmers out here who have sort of grown up using Swift, and they don't even really have to understand how memory management or any of this stuff works under the hood, Sort of this whole history, they're not even aware of it. And so I think Swift is kind of cool in that it's just kind of a functional programming gateway, but it doesn't really, it's kind of been snuck on the whole ecosystem. So where things are going right now, or why we combine these two. PyTorch has historically gone straight from PyTorch into CUDA, so it's compiled directly to NVIDIA. The big push this year for PyTorch, which is another machine learning framework, is they are adding this PyTorch IR, and then this compile time, JIT compilation layer. So basically they're adding an intermediate layer in between their PyTorch and the actual output. Another language, JavaScript, the big push this year has been like, we're going to start doing JavaScript that's going to compile down to assembly. In order to make this even possible, the JavaScript world has been really heavily embracing type safety, and so they're sort of bolting these functional programming paradigms on top of their existing programming language. So what's cool to me is that Google is basically saying, no, we're just going to, we're going to restart our whole project, and we're going to build it from the bottom up on top of a clean functional programming language, which is Swift. And then on top of that, we'll be able to do all this cool tricks. Julia is another machine learning programming language, and they're sort of piggybacking on top of all this. But for TensorFlow 2, the big push this year is to get everything over to XLA. Historically, TensorFlow has not had like a unified linear algebra system. And so Google is saying, OK, we're just going to do everything one way. It may or may not be the right way, but then at least any optimizations we get will be applied to the whole ecosystem. So the second part of Swift for TensorFlow is this MLIR part, which is what the LLVM portion of all this. So essentially, you'll be able to take your machine learning codes, they'll be able to convert it into MLIR, and then you'll be able to output them for whatever device you would like. So the short-term upshot of this is you'll be able to write code once and generate optimized runtimes for CPUs, GPUs, and TPUs. But now there's phones. People are starting to want to build things for phones. This is less of a concern over here in the iOS world. But Android, literally, there's dozens of manufacturers who are wanting to bring different neural network architectures into play. So this gives them a unified system for that. And then the other thing that's cool is that people are literally building new hardware to do machine learning with. And so basically, if you can write a way to get from MLIR to your hardware code, then you can bring the whole TensorFlow ecosystem to your device, which is a pretty cool ability. So this is a slide from Chris Latner's MLIR presentation from a few months ago. But I think it sort of illustrates how all these worlds are sort of coming together. We have various different front-end languages generating intermediate languages, LLVM here, and then at the end, you can imagine it branching back out to, in theory, whatever device you would like. OK, so now let's look at where I think things are going. The first big story, I think, has been cloud computing in general. We used to treat computers as being discrete hardware units, but in the last few years, decade or so, we're increasingly just thinking of them as being computing resources. You might say, I need this amount of RAM, this amount of CPU, this amount of disk space, and a cloud provider can say, OK, here's your machine. Go off and do whatever you would like with it. If we think of, but hardware marches on. So every day, computing is technically getting slightly cheaper, we'll say. So we might think eventually, as the price of computer cycles approaches 0, the amount of resources available to the developer are going to approach infinity. By extension, all these tools basically, they can, in theory, provide you infinite CPUs, infinite GPUs, data, and network access. So the question is, what are we going to do with all this? And the short answer, I think, is nobody really knows. All these platforms are basically saying, we can get you these tools, but everybody's really fighting over, how do we make this easy for developers, because they're expecting developers to actually figure out how to use them. And so right now, I think we're seeing this whole proliferation of tools to deal with various problems at scale. To use an example, we'll say, to pick Kubernetes as a technology, you might say, well, how do you manage a cluster of 1,000 computers? And when the Kubernetes people say, well, you don't. You manage a cluster of 10 computers, and you have your cluster of 10 computers manage your cluster of 1,000 computers. The next trend that we've seen a lot of is just big data and compute in general. The basic observation is that having lots of data really simplifies algorithm design and doing this deep learning stuff. So if you have 1,000 data points, you need to get more data. If you have 1,000,000 data points, you might be able to do some feature engineering on top in order to produce results. But if you have 1,000,000,000 data points, all of a sudden your outliers become entire categories into themselves. And then all of a sudden, you don't have to really use sophisticated approaches. You can just run more and more machines at it. Second big story has been reinforcement learning. And while many people are focused on, say, the algorithms, I think a big piece of the reason why reinforcement learning has had some success recently is simply that we can use these large clusters to generate lots and lots of data and then go back to the first point. The general paradigm, though, I would say in the machine learning world, is that we have lots and lots of single-threaded jobs. It's easy to take one thing, one particular job, and run it 100 times on a cluster, or scale it, run it across 100 machines, but it's difficult to take one job and scale it up to run on, or sorry, it's easy to take 100 jobs and run it across a bunch of machines, but it's difficult to take one job and scale it up to run on let's say 100 GPUs at once. So a lot of the interesting research to me right now is in this area where people are finding ways to break problems apart to where they can be parallelized. But in general, I would say not the fear of the cloud. Many people make a big deal about having large amounts of resources, but I would say that the key is just to know the right path. If you do that, you can keep up with these people with their fancy clusters. So next, let me ask you the question, what is AI? At one point in time, the computer scientists, people, got tired of this question, so they said that reinforcement learning is a subset of deep learning, is a subset of machine learning, is a subset of AI, is a subset of things computers can do, which is a subset of the universe, thus solving the problem once and for all. I'm not going to argue the whole ontology of this or whatever, but this whole idea of defining intelligence as something that humans can or cannot do has always seemed to be a little bit suspect. Likewise, defining things in terms of what a computer can or cannot do has always been sort of a moving goalpost, Computers can't play chess. Okay, well, computers can play chess, but they can't play Go. Okay, well, computers can play Go, but they have to learn from humans. Well, okay, computers can learn Go from first principles, but they'll never be able to play StarCraft, Every year, the pace goes on. I think broadly what we want to do is say that something hard to do is AI, but we don't really know a good way to say that. The flip side, we might say, though, is something not hard to do is not AI. So, does anybody know what 6 times 7 is? You can say it, or 42. Okay. And does anybody know what 42 to the 42th power is? 1 time, what? No, 1 time 10 to the 68th power, so, okay. Nobody in this room can calculate this number, right? So does my phone have AI? I'm confident you all are computer programmers. If you went off with a machine, you could write with the right answer, but you couldn't actually do it by hand. So I think if you look at your answer, if I say, is this AI, you would say, that's not AI, that's just math. The thing is, I think, if you start talking about AI, if I stand up here and talk about AI in the future, where I think AI is going, it kind of sounds mysterious and grandiose, we'll say. Whereas if I talk about math, it becomes a little more, boring or even obvious, We can solve big math problems, but in the future, I think we'll be able to solve bigger ones. We can take some of these bigger problems, and we'll be able to figure out ways to make them smaller to where we could run them on a phone. There's entire areas of math we haven't even figured out yet, and there might be ways of using areas of math we haven't figured out yet to solve problems in math that we haven't even found yet. But conceptually, we can say, once we solve a problem, we can then reduce it down to the smallest possible algorithm or data, so to speak. From there, we take this combination and we move it as close to the user as possible in order to reduce latency. This can be thought of even broader than machine learning, for example. Google builds data centers all around the world to host their web pages. The reason for this is that they know that if you get your results 1% faster, you're 1% more likely to use their search engine, which means they make 1% more money, right? Google programs Gmail in JavaScript. It's not because the Google engineers have a great love for JavaScript. It's because that's the best way to produce an interactive app that runs on your desktop. And so I think long term, ultimately, people wake up with their mobile phones in the morning, people go to sleep with them, right? And so the mobile phone is always going to remain the ultimate platform to solve problems whenever, wherever, and however the user wants. Which brings us to mobile developers. Very broadly, I think one of the basic things about developing for mobile apps is basically we have all these limitations. We don't have as powerful of computers, we don't have as powerful of GPUs, we don't have as much RAM as everybody else. But I think in many ways, these limits make us more creative. We build entire worlds with tiny amounts of resources, right? We work with hardware directly, oftentimes going right down to the machine level. And so we can combine these tricks together to sort of create the illusion of performance. My favorite example of this, for example, is Instagram. You pick a picture, right? You spend a minute figuring out the right emoji to put on there, and then you hit upload, and it goes up to the internet just like that. Many people, I've watched people do this, and to them, it's very simple. That button hits upload, and there it is. But as somebody who actually does this programming, you say, oh, wait a second, that picture is 3 megabytes, and my internet connection has only got this much bandwidth, so it had to have taken at least 5 seconds to upload. How did that work? And the short answer is that Instagram doesn't actually upload the picture whenever you hit the upload button. It started uploading the picture 10 seconds ago whenever you selected it from the camera roll. And so these are the sort of games that we can play to make the machine seem way more powerful than it actually is. And so to me, that's what's cool about being a mobile developer, is that if you understand sort of the magic under the hood, you can play these games in order to create these illusions. So that to me is one of the cool things that we can bring into this whole world, is that if you understand how things actually work, then you can sort of hide them back away again. The second big thing that we can do is that we don't really need to reinvent the wheel. What we can do is take existing cloud and desktop solutions and simply convert them to mobile. So 2 days ago, on Monday, they did the WWDC keynote, and Apple did 2 neural network demonstrations during their presentation. They just didn't call them that, but let's do them right here again just to see them. So here's the first demo they did, right? Pose detection. They did this with the little robots halfway through, if you saw it. And here's the second demo they did, where they were doing real-time scene segmentation on a person and then compositing them into a 3D world. The thing is, both of these demos right here that I'm showing you are JavaScript. The cutting edge part of what Apple did with them wasn't making them run or anything like that. Or sorry, it wasn't building them or anything like that. It was simply making them run fast and making them run on a phone. And so that, to me, is something that any of us can do. Those demos have existed on the internet for literally a year now. Any of you could have found them and been working on them, converting them to mobile. And so to me, this is what we should be doing, is sort of finding these things before the big people do it and do it ourselves. The second thing I would love for us to do is sort of re-examine the paradigms. Many of this stuff exists a certain way because basically it has a legacy code sort of aspect, and we have this opportunity now to rebuild everything from scratch and so rethink how everything is done. So what tools do you need in order to succeed with machine learning? I think functional programming is going to be one of the key factors to all of this. But you have this already if you're doing Swift. So I put a star up here. I think you need the basics of calculus, but enough that you're not afraid whenever people use terms like derivatives and integrals. I don't really think it's, I don't think you need the full-blown, say, college course in this stuff. In the same vein, I think you need some linear algebra You need to be thoroughly familiar with how matrices get multiplied, but you don't need to understand like Jacobian forms or whatever. Another important thing I think you need is just an intuition about users and how they think. But back to the same thing, if you're already developing apps for mobile, you have this already. I think you need to understand real-world statistics, which is less probability distributions and more, okay, this computer gave me this percentage point, how valid is this number? My usual example for this is roulette, but roulette's a little bit boring. So I would say if you want to know all the statistics, just learn how to play a game called craps. That'll teach you a lot. And then finally, I think you need a willingness to experiment. Most of this stuff in our world, Apple and people have developed all these tools down to where you can change a variable and hit run and see the results instantly. Whereas if you go back into this machine learning world, it's very much hit a button and come back in an hour or sometimes a day. So towards this end, I think you need patience. But if you've ever dealt with the App Store review process, you have that already as well. So now I'll try to give you a template for how to get started. Many people in this space will sort of like say, download this API, 10 lines of code, change 3 things here, add your data here, sort of promise you quick results. I'm not going to do that. It's taken me a while to get good at this, and I don't expect it'll be any different for any of you. On the flip side, though, I think if you come into this stuff with the mentality that it's going to take a while, you won't expect instantaneous results. So, if you do a little bit once a week, or once a month even, over the course of a year, I think you can get up to speed with this stuff. The first important trick I think you need to know is Jupyter Notebooks. This is similar to like a Xcode playground, but they run on the web. Google has their own version of Jupyter called Google Code Lab, and it runs both Python and Swift kernels. So what's cool about this is basically you can get started doing deep learning in the cloud for free without really needing to understand how all this stuff works. So let's do a quick demo of that now. So this is just a basic Python running in a Google Colab instance. We'll let it catch up. OK, so we're literally typing code in here. It's going up to the cloud, running it there. And then we're printing out the results, and it's coming back down. A couple of years ago, I did a talk on how to put mobile networks on mobile devices. And so I did a demo using the MNIST data set. So what we'll do now is just copy-paste this demo off the internet and run it in our Google Colab. So here it is running. And if we give it a few seconds, so now we've built a simple computer vision model in order to do the MNIST data set. And like I said, this is running all in the cloud on GPU. It's all abstracted away, but you don't have to actually understand how all the nuts and bolts work to get going. So then, this is a trick many people have not seen, but you can open up notebooks within this thing. So you can go to GitHub, search for FastAI. Ish. And then unjetting. All right, all right. Okay, here we go. Yeah, and you're always messing. Okay. So they have this course. They did a new version of their course last fall. And what's cool then is you can go in here and you can do all these fast AI demos and stuff just using the web editor and stuff right here, so it'll start running. But basically, you can go through all the fast AI courses just using these CodeLab codebooks and then streaming the content off of YouTube. So basically, you can bootstrap yourself for free, or we'll say for the cost of a Google account. So I think this is a super cool trick that everybody should at least be aware of. It's also nice if you find random code off the internet because you can just run it and you don't let them worry about the security implications for you. Okay, I won't watch this. And so yeah, here's the actual code that I'm running on GitHub. I think Google's vision long-term for all this stuff is that we'll be doing everything, a lot of data scientists will be able to do stuff just using code labs. But I think for the here and now at least, you're going to have to do some command line stuff. I took the Fast AI course again this spring. And what they did is they rebuilt the principles of deep learning, we'll say, from scratch. But what was cool is the last two lessons were taught by Chris Latner. So with this, and so they did all this stuff. So effectively, you have Jeremy Howard, who's extremely good at deep learning, and you have Chris Latner, who's extremely good at Swift, working together to give you basically the simplest possible path to get going with Swift for TensorFlow. So towards that end, we'll run the notebook from the Fast AI 2019 deep learning course. So here's where this code is at on the internet. You go into this dev Swift folder. I'm now running it locally, or rather, I'm running it on a remote box, and then we're running in a web browser here. And so now we're going to go to the ImageNet demo. So if you can simply learn how to do this one notebook, beginning to end, I think you'll effectively understand most of the current state of the art for doing computer vision stuff, with Swift even. Anyway, this all runs. Yeah, we don't have to watch it all run, but this is all, like I said, same. It's free. It's on the internet. You can download it. The videos will be released soon, and so I would highly suggest you check out that. Next, if you go through the TensorFlow Swift repo, there's a whole guide to how to download and install Swift for TensorFlow yourself. This is pretty easy to follow along, and they build nightlies and stuff up here, so you can download it there. So what we have here is SIG code base checked out on my computer. So then you need to know basically two commands. This command, which gives you the most recent checkout of the Swift for TensorFlow source. And then this command, which will then build you a fully functioning toolchain. So you can combine these two together to build the whole Swift for TensorFlow code base. It takes a little while to run. But then, like I said, all the code is in here somewhere. So you can go in here, modify it, and make a PR. So then the next thing I would suggest you do is you mess around with this TensorFlow/Swift models repository. They have a number of different examples in here, but we'll look at the MNIST one. So we're going to literally do the We're going to literally run the MNIST demo again. Man. Okay, so we'll run the MNIST demo again. Three, two, one. Come on. Okay, so now we're running the MNIST demo again, but we're running it in the cloud. Well, on my computer remotely, but everything we did in the collab earlier, but just in the command line. They have a number of different demos in here. I would highly suggest you play around with all these. There's a number of interesting tricks in this repository. And then, yeah, here's the guide for the build instructions, how to get your system set up. But I think you can all follow that. So yeah, hopefully if you can do all that, you can make a pull request and you can start to contribute to the project. After that, I would tell you to start reading papers, other people's code, and then most importantly, get out into the real world, find a problem that nobody else has gone after and start trying to tackle it yourself. And then I always, if you can, please try to share your knowledge. It can be as simple as writing a blog post, you can give a talk someplace, or you can simply find somebody else who's interested in this field and try to mentor them however they need help. Okay, very broadly, yeah, I like this quote. It's by Antoine, sort of. He probably actually never said this. He mostly wrote in French, but somebody took, we'll say, some creative liberties in translating his thing, so we'll thank that person, whomever they are, but it's a good quote. Like I said at the beginning, I believe in all this stuff. So, you know, on one level, I could contribute code to these projects. On another level, I can stand up here and give presentations, you know, try to like get you closer to where I think you need to be. But ideally, I would teach you all to yearn for the sea, so to speak. So here's my attempt to do so. I think progress in general comes from like the combination of hardware and software working together. If you look at the original iPhone, it was honestly not that advanced of a phone. There was literally nothing it did that other phones of its day couldn't do as well. If you look at the software of the original iPhone, it was also pretty primitive by modern standards. But the combination of those two things together literally changed the world, and it's literally why we're sitting here today. People have been building computers to essentially play video games for the past 50 years. And in the last decade or so, we've been figured out ways to like harness even just a tiny fraction of that power in order to solve a whole new set of problems that we've never even seen before. And so when the original iPhone came out, I saw it and I said, this is what I should be doing. You know, this is what I should be working on. This deep learning stuff, it came out, and once again, I heard that siren's call, so to speak. And so that's what I've been working on for the last few years. I think that because you all sort of are doing Swift, and I think this whole world is moving to this, I think basically this is an opportunity that's kind of ready-made for all of you. And so, you know, you should seize it if possible. Otherwise, you may, yeah. And so, very broadly then, I would ask you to come work on all this stuff and help define the future of machine learning. and by extension, make the world move faster. So thank you for your time.